What's this? Simultaneous equations. I can solve an equation, but do we have to do two together? What? That's one with the left hand, one with the right hand? What's going on here? Well, it is two together, but it's a little bit different from that. Here's an equation, and if we draw the graph of that equation, we get that straight line. And here's another equation. If we draw the graph of that, we get that straight line. So maybe simultaneous equations means the solution has to work simultaneously, has to satisfy both equations simultaneously at the same time. Okay, so simultaneously, as with most mathematical language, it's unambiguous. Means at the same time. So I guess that's the point we're looking for. When x is 3 and y is 2, that point lies on both lines. It obeys or satisfies both equations together at the same time. So that's what we're about here. Finding a value of x and y that satisfies equations at the same time. What about this one over here? This is interesting because here we have the equation of a straight line. That must be the blue one. And here the equation of a parabola or a quadratic function. We haven't done those before. Is it possible to find a solution to these equations that aren't both linear? One's a straight line and one's a curve. It looks like this time there are 2 points which will satisfy both equations simultaneously at the same time. Do you get it? Simultaneous is the key word. You're working with 2 or more equations. In this course, we will be working with 2 linear equations, two equations that when we graph them give straight lines, linear, if you like. Okay, we actually won't be doing this one with a curve and a line at this stage. So let's go down and see how we might do that. And first of all, what about having a look at a problem which gives rise to why we might have simultaneous equations? Here we are. Let's read this one. Ewan wants to buy a pie but only has $3.50. He sees his friend Andre leaving the canteen with a pie and asks him how much it cost. Andre's not sure because he bought a pie and a sandwich which cost $7 altogether. At this stage, can you work out what each cost? No. We need more information. Ewan then saw another friend, Samuel, with a pie and asked how much it cost. Well, I bought 2 pies and 3 sandwiches and they cost me $17. Hey, this is getting even more complicated. How's he going to work out the balance between the cost of a pie and a sandwich? Can he do it using Andre's information or Samuel's? No, because we don't know the combination of the 2 costs to give the final amount. We don't know. We have to join the equations together and see if we can work out what a pie and a sandwich must have cost to satisfy both situations, both Andre's and Samuel's situation. So here's some mathematics for you. This is handy. Algebra again. If we have an unknown quantity, let a pronumeral or a letter represent it and see where the journey takes us. A pie costs X dollars, sandwich costs Y. Can you see that Andre has 1 pie at X dollars and 1 sandwich at Y dollars, and the total is $7? Hey, this is algebra at its best. We're actually able to find unknowns by making a mathematical sentence. What about Samuel's situation? Well, he bought 2 pies, so it's 2X dollars, and 3 sandwiches, so it's 3Y dollars, and the total cost was 17. We have just been able to make algebraic sentences describe this practical problem. Now, what we want to do is solve these sentences or equations simultaneously, because the value of x and the value of y, value of a sandwich, must work in both equations at the same time. And then we can answer the question. does Ewan have enough money to buy a pie? We better find out what a pie costs first. Okay, here are the two equations. And we've seen from above there that if you drew the graph, the simultaneous solution is the what? The point which lies on both lines. On both lines. Because that means when you put its x and y into either line, you satisfy it. You get the answer 17 or 7. So the point's got to lie on both. Hey, why don't we draw those lines? Now, I reckon the easiest way would be to use technology. But with technology and the Casio and all other electronic devices, you have to have y1 equals. So we're going to have to rearrange this. X has been added to y to get 7. To get y back again, let's take x away. We'll get that. Now that can be put into the graph mode of the calculator. What about this one over here? Y has been times by 3 and then 2x has been added. Let's subtract the 2x for a start and we'll get that 3y is 17, take 2x. Let's then reverse of timesing by 3. Let's divide by 3. And we will have this equation to put into graph mode of the calculator. Later on, we're going to talk about how to draw that by hand. That might introduce some inaccuracies, mightn't it, with thickness of pencil and how well you can plot points. Anyway, let's do it electronically for a start. So come down and let's have a look at the Casio here. So you go over here in the first one, go to menu, hit graph mode, highlight that and hit graph mode. Then we need to enter the functions. Here you can see I put 7 take x and then 17 over 3 take 2/3 x. It must be in this y1 equals format. So there's a bit of work to do there. Then we'd better change the view window of the calculator. How do you do that? We'll come back here, Shift, can you see that? View window, Shift F3. And that will give us this window. And I reckon, from what we've seen before, maybe make the x min 0, the y x max 10, and you can't have negative amounts of pies and that, so we're going to do the same with y min 0 and go up to a y max of 10. Because we were only having 2 pies and 3 sandwiches and that sort of thing, so that should cover it. Then if we hit execute, the graphs will be drawn. Yes. See this point? That's our simultaneous solution. Why? Because at the same time, simultaneously, it lies on both lines. And we could sort of read that off there. 3, I think that's 4, and that's 3 across there. Let's do it electronically. Let's go to Shift, hit Shift, and up here can you see G-solve, graph solve. So hit F3, it'll solve the graph for you. And the first set of options, there it is, stands for intersect. So come in here and hit F5. And if you hit F5, the crosshairs sit on the point of intersection. We were right. It was x is 4, y is 3. So what was x? X was the cost of a pie. So we have actually found it now. That was $4. And y was the cost of a sandwich. And that was now $3. So can he afford to buy a pie? No, I think he's a bit short. I think he only had $3.80, didn't he? Oh, do you remember? I hope you're not getting too hungry now. You'll just have to wait till lunchtime if you are. Anyway, let's go down. And could you have done it by hand? Could you have solved these simultaneous equations drawing your own hand graph? This is what it would look like, wouldn't it? But could you do it? Let's try and plot the first one here. X plus y equals 7. Do you remember? Let's put it up here. X plus y equals 7. Cuts the x-axis when y is 0. If you put that in the equation here, x would be 7. Cuts the y-axis when x is 0. And if x is 0, y would be 7. Can we plot that now? Let's see. Well, cuts the x-axis at y-axis at 7, also cuts the x-axis at 7. So they are those 2 points. And we know from this format up here, it's like y equals mx plus c. It is a straight line. We can rearrange it. We just rearranged it to show that. So you could actually just use those 2 points and join it up. 2 points enough to specify a straight line. Let's look at the other one now. 2x plus 3y equals 17. This line now cuts the x-axis when y is 0. So 2x would equal 17. X would be 17 over 2 or 8.5. Cuts the y-axis when x is 0. So 3y would be 17. Remember, if x is 0, this term goes out, disappears. So y is 17 over 3, which is approximately 5.6, or let's leave it as a proper whole number. It's 5 2/3. This could be a bit hard to plot, couldn't it? X is 8.5. Well, that's not too bad with the scale. 8.5 there. But 5 2/3, see that? This is where graphing by hand has its inaccuracies. 5 2/3 on this scale is hard to find because we've got 2 squares to make a whole. They are 0.5s, each of those. So it's a little bit, see this, a little bit past 0.5. Let's notice now. Inaccuracies occur if you do this by hand. Inaccuracies in a graphical solution. Not so if you do it on the calculator, but if you do it by hand, we have inaccuracies. Very hard to actually plot the points accurately. However, I drew this actually on using a software package, so I have got the exact answer. X is 4 and y is 3. But in practice, that would be very hard to do for those fractional values. Could you please note this? Because what we want to do as budding young mathematicians is actually do it accurately and look at the maths of it. Okay, come on down, and I want you to do some by hand in a minute, and let's just look at what screen clippings from Pearson's have said here. Sketch these 2 equations, so it's in nice format, y equals. So here, the easiest way is y equals x plus 2. That's the y-intercept. And where does it cut the x-axis? When y is 0. So x would be -2. Do the axes-intercept method. And then 6 take x cuts the y-axis when x is 0. That is at 6. That number there. And cuts the x-axis when y is 0. It would be at the number 6. And just join them up. And then this time it works nicely. 2, 4, and you could substitute those values into each equation here and just check there's a solution. Here it is down the bottom. When you put 2 in place of x, you get 4, that checks, and when you put 2 in place of x here, you get 4. Now, they must have both coordinates the same, because at one point, the point is on both lines, and therefore is a simultaneous solution. Implies a simultaneous solution. The one point at the same time is on both lines. Simultaneous solution. Okay, that's our graphical approach. Can you do it, do you think? Well, let's have a look. Here's some from Pearson's, and the answers are just below now. So I want you to try to draw some of these, particularly, I suppose, the ones where it's not y equals, as well as the one where it is y equals. We say that when y equals, we call that an explicit function, where we're explicitly stating the connection between y and x, how to get y from x explicitly. I'd like you to try most of those and then check with technology. Okay, check with technology. The technology will require that you rearrange any expressions into that explicit form. So if you wanted to do this one, you'd have to change it both to y equals to use it. And then at the end of it, just check there, part B from Pearson's here, that the answer actually does work in both equations and then state it. Okay, pause the presentation, have a go. Down below here now I'm going to show you the answers, and then each one you do, go down, have a look at your graph, check the answers before going on. You don't want to perpetuate an error. Let's get it right from the beginning. Come down, let's look at the answers now. Here we are for some of the parts. We'll just go a little bit lower there. And there are our graphs in each case. Check the point of intersection, check the axes intercept. You can see some here, fairly difficult on that scale to do it accurately. So let's remember, some inaccuracies are likely to occur here with this graphing by hand. All right, check your rearrangements as well, and whether you're able to do it with technology. And we'll just put this last one up here, part F there. Down the bottom. Okay, so there you are. Have a look at this one. Did you get that? No solution because the lines are parallel. All right. Okay, mark your work. Have a bit of fun with that. Let's go on. As budding young mathematicians, we want to know, can you do it accurately without a graph? Because fractions on a graph are pretty sus, pretty hard to determine accurately. Let's go down and have a look here. Here we are, we're going to solve equations by elimination. Elimination, I'm going to eliminate this. Oh, what does that mean? Well, what we're going to do is to eliminate one of the unknowns. Eliminate one variable, so I have a resulting equation in just x or y. Can you see that was our problem initially? You can't work out x or y with either of these separately because there's two unknowns there. Change one, you change the other. How do you find out what they are? Let's eliminate one of them. Now what we're going to do, we're going to try to add or subtract the two equations so that one of the variables goes out. Okay, so if you've got two variables and one of them has a coefficient of the same size, we can add or subtract the equations. So let's do that. What have we got here? Well, we haven't got one the same size. We've got 2x here and just x here. So we can actually multiply that equation by 2. Multiply both sides by 2 and write it underneath. Okay, now there's nothing corrupt with that. You call this equation 1, and now this equation 2 perhaps. Now can we eliminate one of the unknowns? Let's try it. Let's subtract equations from each other. Okay, so 2x take 2x, is no x term. 3y take 2y is 1y. Equals 17 take 14 is 3. Hey, we've done it. By combining equations, we have an equation which is solvable because we have eliminated one of the unknowns. So y is 3. So now let's substitute that back into either equation. It doesn't matter. Substitute back into x plus y equals 7. So that means x plus we found y is 3 equals 7. So x equals 4. Okay, so therefore state the answer to the problem. Cost of a pie, this was our original problem, was equal to $4. Cost of a sandwich, always write the answer if it's a contextual or practical problem in terms of what we've got there. Cost of a sandwich, $3. Okay, interesting, isn't it? I wonder if you can see, it doesn't matter which line you substitute back into. Why? The point is a common point or simultaneous solution to both equations. That means no matter what line you sub it back into, you'll get the same other value. Okay, if you're finding y here because you eliminated x, then you'll find an x which fits on both lines. Notice up here, we didn't have to multiply this by 2. We could have multiplied it by 3 and made the y's the same and then subtracted the equations. All right, let's play with this. This is interesting because can you see this is getting at the answer exactly mathematically. Fractions will appear as fractions with this system. We won't have to estimate their position between squares on a grid. Okay, let's go down and see if we can do some. So from Pearson's again, solve the following pairs of equations algebraically by elimination. So let's write the two equations down. And then you can see here that because the y's have the same size number in front, plus 5y and take 5y, if we actually add the equations now, I prefer to put it like that. 3x plus x is 4x. 5y plus neg 5y is nothing. Neg 3 plus 19 is 16. So can you see, if the equations have opposite signs between two variables the variable with the same size value, opposite signs, we will add the equations. Add the equations. Why? Because that will eliminate that variable. We want an equation that only has one variable. Okay? That was our problem before. Any combo could give the numbers on the right. If we have an equation in only one unknown, we've eliminated the variable, then we've got our answer. So here we've got 4x equals 16, divide both sides by 4, you get 4. Now we will substitute it back into either of the original equations. So let's choose this one. So 3 times x, 3 times 4, we found that, plus 5y equals neg 3. So that's 12 plus 5y equals neg 3. Now y has been times by 5 and 12's been added. So let's subtract 12, get neg 15, and then divide by 5 is neg 3. So then you could check the answer in the other equation. X take 5y, just take the left-hand side. So x was 4, take 5 by y, is take 5 by neg 3, and it comes to the right-hand side. So it checks as working in both equations, so it is truly doing it at the same time for both equations. It is a simultaneous solution, and the simultaneous solution, we will state it, is x equals 4 and y equals neg 3. There's no context here. We haven't said x is the cost of a pi or anything, so we can just state the mathematical solution. Let's do some more. This is a powerful technique here. So let's do part B of this question. We have two different equations, 4x plus 5y equals neg 6, 4x take 3y equals 10. Write them under each other. Can you see it? They're the same. If I take this equation away, there will be no x's. 5y take neg 3y. Take neg 3y is plus 3y. And so it's 5y plus 3y is 8y. Neg 6 take 10 is neg 16. Now y has been times by 8. Let's divide both sides by 8. Neg 16 divided by 8 is neg 2. Now we will take our first equation, put in our y, so we've got 4x plus 5y is neg 6. That's 4x plus 5 times neg 2 is neg 6. That's 4x take 10 is neg 6. X has been times by 4. 10's been taken away. Reverse that. Add 10 to both sides. You've got 4x equals, what's this? Neg 6 plus 10. Are you happy? Neg 6, bit rough here. Go down to neg 6 and then back plus 10. You will be at positive 4. Check that out. Divide both sides by 4. X is 1. And we then should check that in the other equation. Okay, into 4x take 3y equals 10, make sure it works. Okay, let's go down now and have a look at another variation. This is like the one I first did with you, where when we write the two equations out, we see we don't get matching x's or y's between the two equations. So if we multiplied, let's say, the top equation by 3, there it is, 1 by 3 to get the next equation, this would give us 6y. And let's multiply the second equation by 2. This is a lot of work. So we want to eliminate one of the variables. eliminate a variable so we get an equation in just one left, and then we can solve it. Eliminate a variable means making the coefficients, that's the number in front of the x or the y term, making the coefficients the same size. It doesn't matter if they're not both positive or negative. We can add or subtract the equations to make it disappear, but we want them to have the same, or not sign, same size, making the coefficients the same size. So it was quite a bit of work. This one here was 2y, this was 3y. So we had to spot multiplying 2 by 3 gives us 6, multiplying 3 by 2 gave us 6. Now we've got to match up, so we can actually add those equations. Let's just scribble this out here. We can add these equations. Let's do that. 9x plus 8x is 17x. 6y plus neg 6y is no y. So if they are the opposite sign, all we have to do is add the equations, and then that will go out. 15 plus neg 32 is neg 17 down here. Let's check that. Go 15 this way, and then from 0, and then neg 32 will be down at neg 17. It's the difference between the two. Now x has been times by 17. To get x back again, you'll divide by 17. So I've got an answer. X is neg 1. Putting it in the first equation, 3 times neg 1 plus 2 times y is 5. That's neg 3 plus 2 times y is 5. What's been done to y? It's been times by 2. 3's been taken away. Let's reverse it. Add 3 to both sides, you'll get 8. And we'll just come down here a little bit, and dividing by 2 you get 4. And then we will check it this time back in the other equation, which is 4x take 3y on the left hand side. And let's stick neg 1 in for x. 4 times neg 1. Take 3 times the y is 4, and we get neg 16, which checks as the right hand side. And so therefore we state our solution either that way or in a bracket as an ordered pair, like a point. Generally we will put it this way because we're rather interested in the separate value for x and y, particularly if that is a variable which we've introduced to represent some practical quantity, like the cost of a pie, cost of a sandwich. Do you get it? You can read what Pearson's is saying down here as well, and I put that in my own terms. All right, let's go down now and have a look at this one. Okay, so have we, hang on, let's have a look here. Have we lost this one? Let's go back to the beginning. Oh, here it is here. Okay, there it is, 2x plus y, 5y, so let's bring that down again. So there's the first one, and the second one is in a slightly different format. So we have to add 5 to both sides to get them in the same format. This isn't bad, this one, because can you see we only have to multiply that second equation by 2, and we've got a match up. Got to multiply them all by 2 though, so it's 2x plus 6y equals 10. That's the top one. They've changed position there. Okay, so multiplied equation 3 by 2, and then put the other equation underneath. Okay, so do you get the idea? We want to match up the size of the coefficient of x or y in both, and then we're going to eliminate it by adding or subtracting the equations. Let's do that now. They're both the same size and sign, so take them away. 2x take 2x to no x. 6y take 5y would be 1y. 10 take 9 would also be 1, so that turned out nicely. Y equals 1. Then let's take the second equation this time and say we've got x plus 3 times 1 take 5 must equal 0. So that means x take 2 must equal 0. X would be 2. Substitute, 2, 1 in place of x and y in here. There it is. And it checks to 9. So we have checked the fact that the solution is truly simultaneous. it satisfies both equations at the same time. Now, in this method, obviously, it's going to satisfy both at the same time because we made up a combo equation, didn't we? We combined the equations here to make a combined equation which eliminated one of the unknowns. But the information that equation contained was information from both the equations. We more or less have made a joint statement, a joint equation here, eliminating one of the unknowns. So, simultaneous solutions must obey both equations. So here then we can write the answer again. All right, are you getting it? Let's go on. And here's some useful strategies. It doesn't matter which variable you choose to eliminate. There you are. If you only need to change one equation to get the same coefficient, do that. So if one's got 2x plus 3y equals 17, and the other one has x take 2y equals 4, hey, we can't make those equal easily. You have to multiply both equations by something. But if you multiply this equation by 2, you'll get that in one multiplication. So try and do that. If the signs in front of one of the variables are opposite, eliminate that variable. Okay, so you might have here, if we made this 2x plus 3y equals 17, and x take 3y equals 4, go with adding those two up and it'll get rid of that one. Think about it, in other words. If the signs in front of each of the variables are the same, choose a variable to eliminate where the coefficients are smallest in magnitude. So you keep the numbers down. Keep the numbers down. If the signs in front of each of the variables are the same, multiplying one equation by a negative number and then adding the equation is often easier than multiplying both by a positive and then subtracting. Oh, I don't know about that. You can think about that. I wouldn't change signs. I would not multiply through by a negative. Okay, that makes it more prone to error. I would multiply through by a positive and then adjust the process by using either addition if the coefficients are different, or subtraction if the sign of the coefficients are the same. Anyway, you can study that and play around in your own way as we do the problems. All right, so here are some problems with the answers down the side here. This is from Pearson's textbook, the Year 10 National Curriculum. So I would suggest you have a go at a number of these. They're all slightly different in each of the sets. Some of them up here have got matching x's or y's, and down here generally they don't. Some multiplications are going to be needed. So there's a bit of fun to be had there. And as you go, check your solutions. Don't perpetuate some error, and don't practice up an error. Okay, so as you do one, glance across and state your answer and see if you got it right. Okay, so pause the presentation now and get into that, and then come back. I'm going to go on now. Hey, well, you're tired now, so I should have told you before, you can do these with technology as well without rearranging the equation. So let's go into the menu, and can you see what I've done here? Highlighted equa, and that stands for equation. So if you execute that, you get this window. And the calculator, this is a Casio 9860 Plus, will handle various equations. Here's the one we want. Simultaneous equations, which is obtained by hitting F1 in there. Okay, and up comes this window. Data exists, ignore that. Somebody's used a calculator before. So do you want to then nominate how many unknowns have you got? Well, in this work with straight lines, we're just going to have two unknowns. So we hit F1 down there because we've just got two unknowns, x and y. Up comes this window, which says they've got an undetermined number of x's, an, an undetermined number of y's, bn, and a number down the end. So then you're going to enter those. So see what's highlighted, the first one. So you enter 1 and execute it. So that'll go there. Then hit 1 and execute it. Then hit 7. What we're doing there is putting in x plus y equals 7. Then keep going. The highlight will go down to the next line and put in 2x plus 3y, and then that'll be 17. Just entered there, executing each time. So we're back to our pie and sandwich problem, which we have just entered those equations. Notice in simultaneous, no rearrangement is needed like it is in graph mode if we have them in this form. Of course, if you have something like y equals 7 take x, this won't work in equimode. So you've got to put that back over. So there's a form for each. You want an explicit function, y1 equals, in graph mode, and you want the general form, ax plus by equals c, for equimode. So nothing's perfect. All right, so if you then hit execute after all the data's entered, here you can see x is 4, y is 3. X is highlighted, so the statement comes down there that x is 4, and you've got the same answer. So there's lots of fun to be had here, and you can quickly check your answers with technology. Okay, let's come down and look at another variation. Solving simultaneous equations by substitution. This is interesting. Now, if one of the variables, here it is written as y equals, that's an explicit form, or x equals, then this is quite a good, there it is there, quite a good method. Because what it's saying is the x and y's of a simultaneous solution both obey both equations. That's what it means. X and y the same at that point in both. It's where they intersect. So you can share them or pinch the x from one and put it in place of the x in the other. Let's look at these two. Now this is not written as y equals, but let's do it. Y equals 7 take x. So we can't solve either of these by themselves because we've got two variables. But if I take this from here and say where the lines intersect, or when I want both of these rules to work simultaneously or together, I can replace that y by 7 take x. So I'm combining the equations not by elimination and making a joint equation by eliminating the variables from both of them, but by substitution in from the other equation. So 2x plus 21 take 3x would equal 17. Just remember expanding that. So we've done it. We've again got an equation in only one unknown. 2x take 3x is neg x plus 21 is 17. Take 21 from both sides is neg 4. Divide both sides by neg 1. X is 4 again. And then we can substitute it back into either of them. But I'll choose the y equals one because that's going to be easier. Y equals 7 take 4 or 3 again. So there's another way of doing it. So one should pick the algebraic method, that's elimination or substitution, which is the easiest in the problem. So this is easiest done if you have y equals or x equals. But mind you, you can change one of the equations to that form if it's convenient. Come on down and let's have a look at another example from Pearson's. Solve the following pair of simultaneous equations algebraically using the substitution method. Okay, well let's take this pair. You can see that y equals 2x from the first one. So let's take the second equation. X plus, instead of y, take the 2x from the top one, equals 18. Quite neatly, 3x equals 18, x is 6. And then substitute it back into the easiest one, which is the y equals one, the explicit statement. So this is 2 or 12, and then check it in the other one. The other equation was x plus y equals 18. X plus y is 6 plus 12 is 18, which checks with the right-hand side. Okay, quite neat. Let's look at the other two. So in the other two here, and there's the solution. The other two, 2x plus 3y equals 4, neg 4, but the other one is written as x equals y plus 3. This is set up nicely to replace in the first equation, instead of x, we'll put in y plus 3. Plus 3y equals neg 4. Again, we have an equation in a single variable. And that's what we were trying to do with the elimination method as well. Equation, a single variable, can be solved. So therefore we've got 2y plus 3y is 5y, plus 6 is -4, subtracting 6 from both sides, 5y equals -10, y is -2. Then going back to the other equation, sticking in -2, we will get x is 1. We should state the solution here, therefore, x is 1 and y equals -2. And check it in that other equation, 2x plus 3y equals -4. Do check that, so let's use the left-hand side. It's just 2x plus 3y. Check it. It is 2 times 1 plus 3 times -2, which is therefore correct at -4. Okay, which equals right-hand side. So we can check those solutions. Right, let's try some of that then. Here they are. Solve the following pairs of simultaneous equations using substitution. So you take the one that is most convenient, got a statement in x equals or y equals, and put it in place of the x or y in the other. Remember, we're trying to get an equation in a single variable. Only one unknown, because then you can see that we can solve for it. The elimination method makes a joint equation where we've eliminated one of the unknowns. This method substitutes for one of the unknowns from the other equation. Have a go at all of these, and the answers are down the bottom. Here we just go down and have a look. There are the answers there to each of those. All right. Pause presentation, toggle back and do all those and check your answers. I'm going to go on now, and here we are using simultaneous equations. What use are they? Okay, what use are they? Well, we're trying to solve a problem involving two unknowns. Pies and sandwiches, or something a bit more sophisticated than that later on. A problem in two unknowns. So to do that, we're going to need two equations, as we saw before with the pie problem. Identify the unknowns and define each with a variable. Let x equal cost of a pie. Let y equal, same thing, cost of a sandwich, that idea. Now, you've got to, if you like, mathematise it, make mathematical sentences for each piece of information. Make an equation or mathematical sentence. If there are two unknowns, you'll need two pieces of information required. Okay, so you have to generate two equations. Solve them simultaneously, only using graph really, if you can use technology. If they say give exact answer or show algebraically, you have to do it with algebra, which is elimination or substitution, whatever seems to be the easiest for the equations you've got. Check your solution by substitution back into the other equation. That's what they mean, not by substitution method. Express the final answer in words. Cost of a pie is $4, cost of a sandwich, etc. Okay, do you want to see how powerful this method is? Algebra is great, and you're well on your way to using it effectively to solve practical problems. Let's come down now and have a look at some of those problems from Pearson's here. Okay, so you can see what they're doing, two unknowns and things in these. You've got to work out what x is going to be, what y is going to be, and then go on. And then here are the answers. State your answers in context. Don't introduce x equals and y equals and then give the answer in terms of that. If x is the cost of a pineapple, the answer up here must be in that context, not in x context. The cost of a pineapple was, etc. Okay, have a look at those. Here's some more down here. And let's go on then. Here are some more difficult ones, reasoning ones. It's a bit of a puzzle there. Of course, later on, in engineering and other areas of science, They won't be just these little puzzle problems. They will be of practical and important use. Here are the answers as you go. So have a go at those. I'll just take you down now to 19. And I think we'll just see if we can get it all on. There, I can't quite get all the answers on. So pause that, have a look. Here are the answers down here. Check it as you go. And I'll just bring up the last bit here of D. There it is. Okay. And then finally, if you really want to test yourself out, have a go at the last little bit here from Pearson's, which are open-ended questions. Here are some sample answers here. There are more than one possibility for these, so check your answers there. Well, look, if you've gotten through this, you should be pretty proud of yourself. Can you see how algebra has exploded? How powerful it can be to solve problems? This is really exciting stuff. So good luck and well done so far. Keep practicing. But for me, for now, it's cheers from me.